Okay. All right, let's start solving some equilibrium problems, okay? You know what I'm going to do? I'm going to skip the first one. So we'll be referencing the practice problems that I posted. I'm actually going to skip the first one because I'm just going to tell you what's going on. We have the same reaction of 3 trials. We have the same temperature. Notice in each trial, we have these are our concentrations of reactants and products at equilibrium, right? So for each trial, we have different concentrations of reactants or products. The equilibrium expression for this system is the crazy, right? Just this is an organic equation. Kc equals the product, C3H7, CO2, C2H5 times H2O. Notice that that's a gas. If it was a liquid, it would not be present. We would literally just omit it. H7, CO2H, C2H5OH. So for each trial, I would plug in my product concentrations over my reactant concentrations. And what you would see for each trial is that K is equal to 4.00. Okay, the point there being that at equilibrium for a given system at a given temperature, the ratio of products to reactants will be equal to the equilibrium constant based on the equilibrium expression. Okay, it does so. The ratio here all turned out to be the same. It's because it's the same system at the same temperature. Let's continue. All right. Now, what we're going to look at is this practice problem right here. We've got another equilibrium system. Let's look at the data. With a closed system, we've got initial amounts of hydrogen, initial amounts of iodine. It is at a given temperature, and they are going to reach equilibrium. At equilibrium, we see that we have a particular concentration of HI, and our job is to calculate Kc. Well, for this reaction, Kc is equal to the concentration of HI at equilibrium squared over the concentration of hydrogen at equilibrium and iodine at equilibrium. All right, so I'm actually going to rewrite this, and this is a perfect time to utilize something called an ice chart, which is often used in solving for equilibrium problems, right? It's a method of organizing data. Oops. All right. So I'm going to go into rewrite my equation. And I'm going to create my ice chart. That's ICE. All right. I stands for initial, C stands for change, and E stands for equilibrium. So it's going to organize what happens in this system from beginning to end. Notice or note that C, the change, is dependent upon the stoichiometry of the reaction. That means the coefficients, the mole ratios. E is the concentration at equilibrium. You need to realize that I plus C yields equals E. All right, let's plug in our data. Initially, we've got some hydrogen. And guys, I have done this. I am literally going to get rid of those extra zeros there. It just takes up too much space. Just pretend that they're not there, okay? I'm just doing that for the sakes of this problem and the space I have on my paper. So I do have some hydrogen. That is 1.00 times 10 to the negative third molar. I do have some iodine. That is 2.00 times 10 to the negative third molar. And I'm left to assume that I do not have any product initially. I do see that at equilibrium, I have some product, and that's 1.87 times 10 to the negative third molar. Now, this reaction obviously went into the forward direction because I didn't have any product, and now I do. So I know that I lost some reactant. I lost 1x because the coefficient. I lost 1x because the coefficient in front of I, and 2 is a product, so I gained it, and I actually gained 2x. So remember, I and C make E. At equilibrium, for hydrogen, I know that the concentration will be the 1.00 times 10 to the negative third minus x. For iodine, it will be 2.00 times 10 to the negative third minus x. And I know for the hydrogen iodide, it is 1.87 times 10 to the negative third. So I need to solve for K over here, right? My job is to get my equilibrium constant. That means I need to know all of my equilibrium concentrations. That means I need to be able to figure out what X is, all right? Well, look right here. I plus C equals E. So that means that 0, I'm going to pull this down here, 0 plus 2x equals 1.87 times 10 to the negative third. All right? That means that 2x, I'm just going to jump ahead. That means that x is equal to 1.87 second e negative 3 divided by 2, 9.35 to the negative fourth. Okay, these are all molars. So I'm going to plug that in here, and I'm going to plug that in here, and I will then know all concentrations at equilibrium. So the concentration of hydrogen at equilibrium is equal to 1.00 times 10 to the negative third minus 9.35 times 10 to the negative fourth. The concentration of iodine at equilibrium is equal to 2.00 times 10 to the negative third minus 9.35 times 10 to the negative fourth. Solve for those. 1 second e negative 3 minus x, 6.50 times 10 to the negative fifth. 2 second e negative 3 minus 9.35 second e negative 4 is 1.06 times 10 to the negative third. Okay, well, I need to solve for K. K, as we've already written, is equal to the concentration of HI at equilibrium. That is 1.87 times 10 to the negative third, and I need to be sure to square that. I need to divide that by the concentration of H2, 6.50 times 10 to the negative fifth, and 1.06 times 10 to the negative third. Once I do all of that, I will get 51. No units need to be there. Okay, so we knew some concentrations at the beginning and some concentrations at the end. Proceed. Okay, another reaction. We've got two, hold on. Here we've got 2AB yields A2 plus B2. All right. 2 moles of A and B in a 10.0 liters. That's going to yield a concentration that is this many molar. And that's of A and B initially. So I, C, E, 0.200 molar, 0.200 molar, 0. This reaction will go in the reverse direction, okay, because we don't have any reactants. So I know I'm moving in the reverse direction. Notice there's some more data that I'm provided. That is the concentration of A and B at equilibrium. So I may as well write that right here. And now, what do I need to solve for? What is the value of K? Well, K will be equal to the concentration of A times the concentration of B over the concentration of AB squared at equilibrium. let's plug in our C. We know that we are gaining reactants, and that will be 2 for every one A and every one B. Right, we're going in that direction. Therefore, this is 2x. 0 plus 2x is 2x. I can pick one of these. Oops, I didn't really want that, but I'll just keep it to solve for x, right? What I see is that 0.200 molar minus x equals 0.130 molar. Therefore, x must equal 0.070 molar. And therefore, 2x is equal to 0.140 molar. And I will plug that in for that. So I know that the concentration of AB at equilibrium is 0.140 molar. So I now know the concentrations of all species at equilibrium. I know my products, and I know my reactant. And I can plug those into my K expression. I'm just going to do 0.130 squared, because it will be multiplied together, over 0.140, which is squared due to the equilibrium expression. 1.3 squared divided by parentheses 0.14 squared equals, it's not right, 0.13 squared equals, divided by parentheses 0.14 squared is 0.86, and it looks like we have 3 sig figs for this problem, so 0.862. Less than 1, more reactants and products at equilibrium. Close to 1, so similar concentrations. Okay, let's continue. Okay, at a given temp, the above reaction K is 4.60. Okay, so 2AB yields A2 plus B2. K equals 4.60 equals A2 B2 over AB squared. All right, we have 5 moles of AB, and it's in 20 liters. So 5 moles divided by 20 liters. 5 is a quarter of 20, so this is going to be 0.250 molar. AB is placed, so that is initial. Allowed to reach equilibrium, we're left to assume there's none of this. What is the value of all substances at equilibrium? And what is the percent dissociation? I'm actually going to pull these up because I know I'm going to need my space. Okay, I will go in the forward direction. I have no products. I need to form some products. I will lose 2 x's. I will gain an x. I will gain an x. Therefore, this is 0.250 minus 2x. This is x. This is x. I have no way of solving for x using my ice chart. Right? Like, I can't. So what I will do is I will plug my variables into my equilibrium expression. All right, we've got 4.60 equals x times x over 0.250 minus 2x. What you need to see is that is, and that's squared. 4.60 equals x squared over 0.250 minus 2x squared. Now what's happened is we have a perfect square. If we did not, then we would have to utilize our quadratic equation. You may run into that problem, but on your AP Chem exam, you will not be utilizing quadratic equations. But some equilibrium problems require the use of a quadratic equation. All right, so in order to get ourselves out of this perfect square and keep us from needing a quadratic equation, we will simply get the square root of both sides. okay? So the square root of 0.460, now, I'm not going to round in solving this problem, because if I do, and I go and check my work, then I will not get 4.60, all right? So I have learned that I'm going to keep lots of values. Square root of 4.6 is 2.14476. That's equal to x over 0.250 minus 2x. Do your math, fast forward, come back, or hang in there with me. All right, that's two, don't round. 2.14476 times 0.250 minus 2x equals x. Let's start breaking this down. So I've got my 2.14476 in my long, all of it's still in here, times 0.25. So that's going to give me 0.53619, and I'm going to stop there because there's a 0 after that, minus 2.14476 times 2 equals. So that's minus 4.289. I'm going to keep it all, equals x. All right, let's simplify it. 0.53619 equals 5.28952x. X equals 0.53619 divided by 5.28952 equals, and what I have is x equals 0.101368. Okay. Okay. So let's look at what we have. We now know what x equals. All right. I can plug that in for this, this, and this, and I will have all of my equilibrium concentrations. So for AB, at equilibrium, we have 0.250 minus 2 times x. We said that x is 0.101368. 0.250 minus parentheses 2 times, and I still have that number there. Okay, I've got, if I did that right, I think I did. I've got the concentration of AB is equal to 0.0472633. The concentration of A will be equal to the concentration of B, and that will be X, which is 0.101368. Okay. Now let's, we got our answer. We've got our answer. What is the value of all substances at EQ? Well, I would now round that, right? I would say 0.0473, and I would say 0.101. Okay, and now we need to know what is the percent dissociation of AB. Students get confused with this. This is not hard. Look at AB, right? Let me change that color. Here's AB, all right? Let me get rid of some of these highlighters. All right, now we had this much, oops, don't do that. We initially had 0.250 molars concentration of this compound. In the reaction, it itself dissociated. What percent dissociated? Well, we lost, of our 0.25, we lost 2x. So essentially, the percent dissociation of AB is equal to the amount lost, which is 2x, over the original amount, right, which for us is 0.250, times 100 to get that to be a percentage, right? All right, so go ahead and plug that in your calculator, times 100. So the percent dissociation is equal to the amount lost. That's 2x. That is 2 times 0.101368 equals 0.202736. Yes, I'm keeping everything over 0.250 times 100. So divided by 0.25 equals times 100 equals, it looks like I have an 81.1% dissociation. And that makes sense because most of it went that way. All right. And I believe we will stop there for now. Okay, great. Stop and end.